In this problem, we're going to start with the ideal gas of 1 bar and 75 degrees C, and we're going to compress it adiabatically and reversibly to 47 bar, and the question is, what's that final temperature? So, first thing to point out is the diagram is not to scale because clearly the final volume is going to be much smaller when we're going to pressure 47 bar. Of course, the temperature is higher than 75 degrees. Okay, so the way we do this is we write the entropy change, the differential entropy change for an ideal gas, and that's Cp over T dt minus R dP over P. And of course, the entropy change is 0 for an ideal gas. So if we integrate this, we have integral Cp over T dt minus R, and integrating this, we have log of P2 over P1. And that's equal to 0 because it's reversible and adiabatic. So this is going from T1 to T2. Now I'm going to write the heat capacity in terms of a temperature-dependent heat capacity with constants. So I've moved the pressure term to the other side of the equation. Now I can do the integration, and integral of A over T is going to be A times the log of T, and so if I substitute the limits, T2 over T1, B, T cancels, so this is B times T2 minus T1, and C then times integral of temperature would be temperature squared, so T2 squared minus T1 squared. And the last term, D over 3, as we integrate T squared, T2 cubed minus T1 cubed. And this is all equal to R log P2 over P1. So now what I'm going to do is substitute in the numerical values. I'm going to look up heat capacity for carbon monoxide. So let me pause and do that substitution. So I have constants. A, for example, is 30.87. Gas constant 8.314. So I want to solve for T2. I'm going to use solver in Excel, and I get T2 is equal to 988 Kelvin. So I should point out 348 is 75 degrees in Kelvin. And so I have the final temperature. Now I can get the work, because the work, so dW equals du for adiabatic process, and du is CV dt, which is CV is Cp minus R dt. And so then work is the integral Cp dt minus R integral dt. And now it's a matter of substituting in A again and doing the integration. So let me pause and do that substitution. So I've done the integration and substituted in the limits. This is the work, reversible process. And now I'll just substitute in the numbers, the constants A, B, C, and D, and the initial temperature in Kelvin, 348. So let me again pause and make that substitution. So substitute the final temperature we calculated and the initial temperature both in Kelvin, and so I can just do the arithmetic to determine the work. 14,534 joules, which 14.5 kilojoules. So this is the work for this adiabatic reversible process where have an ideal gas, but the heat capacity depends on temperature.